So this is a short video about some of the observations I've made by using a three-dimensional structure model with sw4. So the problem I want to discuss in this particular video is this kind of a pattern. So let me just describe what the problem actually is. So sw4 does allow us to actually account for topography. So that's a very good thing, right? So here it's actually a map view of the topography for a simulation box at the Blair watershed. That's one of the inversions that's done in wave 1 stasis. Um, so that's gonna give you the topography, and this topography was created by adding a few lines of input in the uh, add a few lines of instructions in the input file for sw4. So here it's showing how to extract images from sw4. Here it's map view plots for topography, and then latitude and longitude, and then also the VS, so shear velocity at zero depth. So z equal to 0 just means that it's a 0 depth. And then if I want to look at the cross sections, suppose I want to look at the cross section at x equals to 135. The reason that I picked up x equals to 135 is because the entire grid has x equals to 270, right? 270. So the midpoint is 175, right? So x equals to 135, and then all the generated file is going to have a prefix that's called a test. And then for the cross sections, I want to look at the PSN density. So I mean VPVSN density. So that's how you extract the structure model from sw4 to look at what the structure model actually looks like inside of sw4. So once you have finished running sw4 using this particular input file, you're gonna see a bunch of those files, those test.cycle, these files. These files were created by sw4 and contains the images, the map view plots, and also the cross sections. So if I want to make a plot of it, I wrote a script for that, right? So I have to add the tools inside of the sw4 and then my own scripts. And then if I want to read any of the images created by sw4, I have to use the read image function that's provided by sw4 tools. And then I have to specify the file name. Here I'm constructing the file name based upon some prefix, and then also so these lines of code are gonna allow me to read the inputs, to read the images created by sw4. This is plot topo underscore map.m. That's one of the scripts, and inside of my BW scripts subdirectory. So and then I read in the image, right, and then I convert the longitude and latitude into easting and northing by using UTM. That's degree to UTM is like a meta function I downloaded from the web. So that's gonna allow me to convert longitude and latitude into easting and northing. And then I make the plot here. Right. Yeah, that's plotting the topography. That's the first subplot. That's plotting this topography. That's gonna create this particular figure, right? And then I also want to look at the shear velocity, VS, at 0 depth. That's also a map view, right? And the shear velocity, that's gonna it's gonna look like that. It looks nothing like what I was expecting, because the three-dimensional model that I used as input um, doesn't have this kind of fringe pattern. This kind of patterns looks almost like those those interference patterns caused by uh, the wave effect of light, that kind of thing. Um, right. This kind of fringe pattern is not supposed to happen in an ordinary three-dimensional velocity model, right? The topography looks completely smooth, but the shear velocity model that I used as input is not supposed to look like that, especially on the boundaries, right? This is actually the boundary used for it's actually a absorbing boundary. So for this absorbing boundary, it's supposed to be a constant velocity at each depth. So this constant velocity is supposed to increase with depth, right? It's the average of the velocity at that particular depth. So it's supposed to be a constant, right? But nevertheless, it has variations inside them. So why do I have that? Why do I have that? Right. And then if I want to look at the cross sections, this is map view at 0 depths, right? But sw4 doesn't allow me to extract a map view at different depths. It only allows me to extract a map view at 0 depths, right? So if I want to look at the map view at depths that's deeper than 0 depths, then I will have to write my own codes. And then that's the cross sections. Here I'm reading the cross sections, right? Because it's got two subgrids. One of the subgrid is the curvilinear grid used for accounting for topography, and then there's another grid that's underneath it. It's a uniform grid. It's a uniform Cartesian grid used for actually the calculations for underneath the grid. So there are two grids, and then if I want to read the images for different grids, I have to sort of do. This is for the first grid, right? So the second input to read the image is 1, and then the second grid, that's 2, right? And then I read the different grids, and then different VS shear velocity for different grids, and then I try to plot them together, right? So I could assemble them first into like a one matrix, and then plot that assembled matrix, right? But here it's plotting them, and then the cross section is going to look like this kind of thing, right? So that's where the boundary actually is. So the boundary is supposed to be the boundary velocity is supposed to vary only with depth, right? It looks like it's almost like that, but there are some kind of jumps, those bumps, those bumps, right? Those are small bumps. Makes it look like it's not exactly varying with just the depth, right? And then inside of this region, it's supposed to be a three-dimensional model, so it's supposed to have a smooth variation that looks like three-dimensional, right? And then the velocity model was created by Wei using the discontinuous Gregorian code, using the inversion code based upon discontinuous Gregorian. It's also, right? It's not exactly smooth because you can sort of see those blocky features, right? It's not a smooth model. It's a blocky model, right? Looks nothing like the smooth images that we actually used in the DG code, right? And then if you look at the surface, the velocity model close to the surface, again you sort of see this kind of bumps, right? It looks like the color didn't change too much, right? But if you pay attention to the shades of the color, this is from like the lowest velocity to like the variation could be like over 100 actually, right? So this is actually quite a big jump. The unit is in meter per second. So this is a quite sharp discontinuity. It's like a for near surface, this is a very big velocity change, right? The different shades of blue actually tells you it's actually quite big changes in terms of velocity, right? But why do I get that? Why do I get that? So here are some experiments that I did. What I think, I don't know for sure, but what I'm guessing is that it's caused by the interpolation routine inside of sw4. And the interpolation routine is actually expecting a velocity model that's relatively smooth. Not only smooth in the lateral dimensions, but also quite smooth in the vertical dimensions. In fact, it's expecting a velocity model that's actually, it's supposed to be smoother in the vertical dimensions than in the lateral dimensions, basically. That's what I think. That's what I'm guessing. Maybe I'm wrong, but that's one of the experiments that I did. That's one of the experiments I did. So the code that I used for making this, for doing these experiments are listed here. So here that's the reading from the original three-dimensional VS model, right? So IX0, IY0, and IZ0 are indexes into the VS area. That's the input file. That's the input three-dimensional shear velocity model. This I0 is supposed to be computed based upon topography. So I0 equals to round depth below topo divided by the vertical sampling interval. That's like 1 meter, I think, right? For this particular example. So depth below topo is actually computing so here I'm actually extracting topo reference from this topo in box, right? So this topo ref is supposed to change from based upon the lateral location IX0 and IY0, right? So at different lateral location, the topography is different, and then topo ref is going to be different, and then depth below topo is going to be z subtract topo ref, right? So this z is actually referenced to a z ref. Z ref is like the highest point in the topography for this particular box. In this particular box, the highest topography is like a minus 16 meters, right? So the vertical direction is pointing down, right? So it's supposed to increase downward, and then everything above zero is like is going to be negative. So here it's actually plotting the negative of the topography value. So it's supposed to be like a minus 16 or something. So z ref is like the highest point in the topography inside of this particular box, and then z just equals to this reference topography plus a grid spacing times Iz. So this R file that I'm actually trying to create, it's a three-dimensional R file format used by sw4 that requires some kind of a description about the velocity block, right? The three-dimensional velocity model. And then the R file has a format that's how do I say it? It's a three-dimensional cube. It doesn't have topography built into it. It doesn't actually it has a block for describing the topography, but the velocity model is supposed to be a three-dimensional rectangle that doesn't have topography information. The only thing you can use for describing topography is to actually set the value that's above topography to be minus 99, 999, that kind of thing, right? So everything below topography can have normal VS values, positive VS values, but everything above topography has to be some kind of a completely wrong number, right? And then here it's like here Iz is actually supposed to actually go through the three-dimensional rectangle rectangular box, right? So here inside of this z loop, I have to actually compute the interface between the topography, the interface. I actually have to compute the topography, right? And then everything below the topography is gonna be inside the depths below topography, and then above it I have to sort of assign some minus 999. So this beta alpha rho, these three arrays that's gonna be used by sw4 are initialized to minus 999, right? And then all the values that's going to be changed are actually at depths below topography, and then that's going to be assigned by VS, right? So what I did was to actually look at some kind of a, suppose I change the velocity model to something like that. So if I0 is actually computed based upon depths below the topo, right? So it's gonna be the index corresponding to depths below topo, right? The nearest index corresponding to depths below topo. And then the VS that I got from Wei was actually referenced to topography. It's not referenced to zref. It's not referenced to like a minus 16 meter or something. It's a reference to topography. So all the values that I'm using here is actually referenced back to topography. So IZ0 has to be IZ0, when IZ0 equals to 0, then that's exactly at the topography. And then IZ0 equals to 1 is like 1 meter below topography. So IZ0 is actually computed based upon depth below topo, and then I use IZ0 to index into VS, right? So the experiment I did was here, right? So suppose I change IZ0. So if IZ0 is smaller than 2, which means that IZ0 has two values, 0 or 1, right? When IZ0 equal to either 0 or 1, it's going to have a constant value of 342. And then everything larger than or equal to 2 is going to have a constant value of 352. That's like a 10 meter per second higher, right? For like a 1 meter increment in depth. And then the images I'm gonna get is gonna look like that. It's gonna look like that. So you don't see those fringe patterns anymore, right? You see some kind of interruptions, some kind of noisy patterns close to those blocks, right? Close to those locations, right? But it doesn't actually show you any of the variations are actually quite small, from 342 to 346.5, maybe 347 something, right? 347. 342 to 347. That's 5 meters per second, right? That's exactly half. That's exactly half of the variations in the vertical direction, right? You see some of the grid points actually has values that's going up to values between 342 to 347, between those red blocks, right? And then that's the cross section. That's the cross section, right? This cross section is at x equals to 135. That's this direction. That's this cross section, right? And it looks like that. It looks like that. So at zero depth, so at zero depth below topography, it looks like it's relatively uniform, right? It's 342, right? And then so this is like a one grid point, right? Yeah, that's like one grid point, and then that's another grid point, and then that's another grid point. Don't forget, in my input, it's a IZ0 equal to 0 or 1. You're gonna have 342, right? That's 0. This is 0, right? And then this is 1, right? 0 is still like 342, but 1 has RZ 0 equals to 1 is gonna have values that's between 342 and 352, right? And then everything larger than or equal to RZ 0 equals to 2 is gonna have a value of 352, right? But it's not like that. It's this is 0, this is 1, right? 1 is supposed to be 342, but it's not. It's some value between 342 and 352. And then 0, 1, 2, this is 2. 2 is supposed to be actually 352, right? But it's not exactly 352 because this is 352. But so this value is like between 42 and 352. So these two layers of grid, is not going to be exactly the same as what I specify in my velocity input, right? And the reason that I'm seeing that is because the interpolation routine inside of the sw4 is doing some kind of a smoothing or smearing in the vertical direction, right? So it's not going to use the exact values that I used as input. It's going to do some kind of a smoothing in the vertical direction. That's going to pull high values from larger depths to shallow depths. And then it's going to push down lower values in the shallow depths to larger depths. Right? It's going to do this kind of vertical mixing. And then that's what's actually happening here. That's what's actually happening here. The fringe patterns is caused by especially on the boundaries. Those fringe patterns are very clear, right? Also in the interior, right? It's because it's actually pulling larger values from larger depths to shallower depths, right? So the three-dimensional model actually increases very fast with depth. And sw4 is actually taking those very large values at 1 meter below the surface to the location of zero surface, right? And that's why you see these fringe patterns. It's related to the interpolation routine used in the sw4. So how do we actually deal with that, right? You have to actually use relatively smooth models. So it cannot actually increase very fast with depth, at least at the 2 grid cell scale, right? So the velocity model has to be smooth with respect to 2 grid cell. 2 grid cell, this kind of length scale, right? Especially in depth, actually, especially in depth. So the velocity model cannot have huge gradients with depth. Otherwise, you're going to see these kind of fringe patterns. Yeah, I will need to do more investigation about this particular problem. Maybe it's a problem, but maybe it's not a problem. It's required by this particular finite difference algorithm that's needed in order. That's the reason that they are doing this kind of smoothing is probably just to make the calculation scheme stable, right? If you have very sharp discontinuities, it's gonna destroy the stability of the algorithm, right? So the code is not gonna, it's gonna give you not a number or infinity values in a very short amount of time. So that's why they are doing this kind of smoothing inside of sw4, right? But that's a shortcoming. That's a shortcoming of any kind of a numerical algorithm for solving the wave equation. Not just the finite difference, but also the DG code, the discontinuous gradient code, right? Any kind of model, any kind of code will have this kind of restrictions, but different algorithms has different tolerance, right? To some extent, maybe DG has a larger tolerance, right? This is like 2 grid cell. 2 grid cell. Okay, so that's this particular problem.